Lab 2, Motion of a Falling Object. This lab focuses on the situation of Newton's second law, in which there is a non-zero net force, meaning the initial velocity and the final velocity will not be equal. With a non-zero net force, the velocity will change over time, causing acceleration. In this lab, I observed an object in motion falling from rest until hitting the ground. In my case, it was a paper ball dropped from my height to the floor. Using tracker, a paper ball's travel was tracked from the rest to finish and created an observed model. Using the data from tracker, I plugged in the data to VPython, finding a computational model of the paper ball's motion only accounting for the gravitational force, followed by a computational model accounting for the gravitational and drag force. Using the data from the models, I created a spreadsheet and a graph to compare the results. After comparing the data, I concluded that my observations of motion of the paper ball proves that there was an unequal force acting on the ball. Therefore, the net force was not equal to zero and the paper ball was accelerating downward. The best model for this lab was the computational model in which the drag and gravitational forces were accounted for. The physics of this lab focuses on Newton's second law, in which the force is equal to mass times acceleration, as well as the final velocity is equal to the initial velocity, plus acceleration times time. Some other physics concepts that were used were the weight force, which is equal to the mass times gravity, in which gravity is equal to negative 9.8 meters per second squared in the y direction. The weight force pulls the object downward because of the gravitational pull. There's also the drag force, which is equal to the constant v multiplied by the velocity squared. The drag force is the force acting on the object that pulls it upward. In the tracker model, the x-axis was the horizontal axis and the y-axis was the vertical axis, with the origin being at the paper ball in the first frame. With the data collected, I added it to the spreadsheet to compare to the future computational models, as well as found its initial position in the x and y positions to plug into the computational model. The previous slide showed the code of the two computational models. On the left, the net force only consisted of the gravitational force. On the right, the net forces included the gravitational force and the turbulent drag force. A similarity between the two computational models was the initializations, which includes the force of gravity and the paper ball's initial position. Differences are the inclusion of the drag force equation, the drag force constant, and the drag force being included in the calculation of the net force. All the data was collected from the models and put into a spreadsheet, and this graph was created. The blue line is the data of the gravitational force. The orange line is the data from tracker. The gray line is the data from the gravitational and drag force. My drag force was very small because my paper ball was too small and dense, decreasing its surface area and making it too aerodynamic. Therefore, the two computational models were almost identical on the graph, which were the blue and the gray line, which almost overlapped. Other errors include my camera being slightly tilted and not being compensated by tracker, as well as not tracking the exact center of the ball every time because of having a blurred image of the object as it fell, causing myself to question where the center of the ball was. The what does it mean question asked me to examine a velocity versus time graph and decide which model predicts the terminal velocity. The computational model that includes the drag force predicts the terminal velocity because the sum of the drag force and gravitational force will equal zero at some point, creating that terminal velocity. The tracker model may predict the terminal velocity, but more data is needed to be collected to prove to see if the velocity ever stops changing. The computational model without the drag force did not predict the terminal velocity because there would be no forces opposing the gravitational force. If I threw the paper ball downward instead of letting it go, the same terminal velocity would be reached. The gravitational drag forces would still cancel out, so the same terminal velocity would be reached, assuming no other forces would be acting on the ball. The time it takes for the object to reach its terminal velocity will vary due to how hard I throw the paper ball, since it would have an initial velocity compared to just dropping the ball with no initial velocity. My answer is supported by the following computational model's graph. I changed the initial velocity in the y direction from 0 to 10 meters per second downward, which increased the speed of the paper ball at the beginning of its motion, shown by the ball further away from the start than with a 0 initial velocity. That is all, and have a nice day.